Today we're going to continue on with Chapter 7, today looking at Polygon Similarity. So by the end of the day, you'll be able to answer the following questions. What makes images similar? What makes images non-similar? And finally, what makes triangles similar? All right, so by the end of the day, you'll be able to use the facts we're going to learn about similar polygons to solve the problems. You'll be able to do the following things. To find the missing length of a side of one of two similar polygons, to find the missing length of a side of a triangle with a segment parallel to one of the sides, and finally, to find the variable and expression that makes two polygons similar. All right, so before we get started, let's talk about similarity. Things are similar. For images to be similar, they must be proportional. So let me show you what that means by starting with an image of a cow. So here's a cow. Now I could take that cow and I could manipulate that image in lots of different ways. I could make it bigger. I could make it smaller. I could take it and I could rotate it around. I could take that image of a cow and put it in a mirror and reflect it. I could even do a combination of things like make it bigger, rotating it, and reflecting it. But in all of these 5 examples below, all of them are proportional. So they are similar images. What I mean by proportional is that every time I changed the image, anytime I made the image X% taller, I made it X% wider. So in that bigger image, for example, let's say I made it twice as tall, well, I also made it twice as wide. In that smaller image, I made it whatever, 1/3 as tall, so I made it 1/3 as wide. But in all of those green images, all those images that I've shown so far, the ratio of the cow's height to its width is proportionate to the ratio of the height to the width in the original image. The ratio has stayed the same. The images are proportional. That's what makes things similar. They're the same shape, even though they might be different sizes or different orientations. Okay, let me show you some images that aren't similar. So if I take that original image of a cow and I make it wider, but not taller, now you can see how that image is not the same shape as the original image, or all those ones in green. I could do the exact opposite and make a basketball playing cow, a cow that's much taller but not any wider. In both of these examples, these images are not similar because they're not proportional. As I've changed the dimensions in one dimension, either width or height, I haven't changed it proportionately in the other way. So as a result, the images are not proportional, so they are not similar. Let me show you another example you might be aware of, which is that if in your computer, when you click on an image, it puts this box around it. And if I just grab this image and I pull on it, I can make it any size I want, but you'll see that I'm not obviously making these images similar because, go back to my original image here, this image here, the ratio of the width to the height is obviously not the same as this triangle here, the issue of the width to the height. Okay. However, because computers know that we sometimes need to keep images similar, think about when you've posted a picture online or you've seen a picture online where someone hasn't done this and all of a sudden their face gets fat and or too thin, right? Either they stretch their face too wide or they stretch their face too tall. In either case, it doesn't look like them. So on a computer, if I hold down the Shift key, which I'm doing right now, and I grab this image on the corner and I pull on it, no matter where I pull, it's going to stay similar. The ratio of the width to the height is always going to stay the same. And since computers know that I can flip it, I can take a reflection of it, but the ratio of the width to the height is always the same because I'm holding the Shift key. As soon as I let go of that Shift key, now all of a sudden I can change it to something different. And so that is another way you can think of similarity, is that by holding the Shift key, it keeps all the images similar on your computer. All right, let's take some notes here. All right, so similar figures are figures that have the same shape, but not necessarily the same size. And two polygons are similar polygons if the corresponding angles are congruent and the lengths of the corresponding sides are proportional. So the ratio of those sides is going to stay the same. All right, the symbol for similarity is, you'll see the symbol above there for congruency. We have an equal sign with a squiggly thing over it. So a symbol for similarity is just that squiggly sign. And so on the right here, we can read that we say that quadrilateral ABCD is similar to quadrilateral GHIJ. And so if that's the case, then the first part, the corresponding angles must be congruent, is true. So what does that mean? Well, that means that A is congruent to G. Also, like congruency statements, the order matters. So A and G are both in the same place, and I can see on my diagram that they're both right angles. So in this case, A is going to be congruent to G. My second part of my statement is B and H. Those are in the corresponding places, so they must be congruent. C and I are in corresponding places, and I can see on my diagram they are congruent. And then finally, D and J, which again on my diagram they both have 2 marks. I can see they're congruent. They're in corresponding places, so they must also be congruent. And the second part of my similarities says that the lengths of the corresponding sides must be proportional. So that means, in this case, that the length of the side on the left, AB, and compared to the length of the side on the left of the big one, GH, that ratio is the same as the ratio that's created by the sides on the top, in this case, BC over HI, which is the same proportion, so the same ratio or equivalent ratios as the sides on the right slanting down, so that would be CD compared to IJ. And all of those ratios are proportionate to, or the ratios have the equivalent values to, the side on the bottom, DA and JG. So the ratio of all of these is the same. We talked before about an extended ratio is a comparison of 3 or more things by division. So an extended proportion is simply 3 or more ratios that are equal. So for example, the thing we have above here is an extended ratio because we have, in this case, 4 equal ratios. Finally, we have something called a scale factor, and that is the ratio of the corresponding linear measurements. So what is the ratio, for example, AB to GH? What is the size of that smaller triangle, or excuse me, that smaller quadrilateral to the big one? Let's do a different example here. I've got these 2 rectangles here, LONM and SVUT. In all the sides on the triangle to the left, so LO for example is 5, I multiplied by 3 to get the corresponding side on the right. So 5 becomes 15, 2 becomes 6, 5 becomes 15, and 2 becomes 6. I multiplied each of those sides by 3. So we would say that the scale factor of quadrilateral LMNO to quadrilateral STUV is 3, or 3 to 1. For every 3 inches I have on the STUV, I've got only 1 inch on LMNO. All right, so let's try example problem number 1. In this example problem, it tells us that triangle LNP is similar to triangle SRT. So what are the pairs of the congruent angles? Well, again, similarity statements are like congruency statements. The order matters. So M and S are both first. The fact that they're first doesn't matter, but they're in the same place. So I know that those must be congruent. Also, if I go and look at the diagram, I can just see that that M and S are the only 2 obtuse angles there. So again, they must be corresponding. They must be congruent. The similarity statement shows me that N and R are both second. So they are in the same place. They must be corresponding. N must be congruent to R. And finally, P and T are in my similarity statement in the same corresponding place, in this case last. So P must be congruent to T. The second question it's asking is, what are the extended proportion of the ratios for the corresponding sides. So once again, let's put on some sides here. L, M, and RS must be equivalent because those are equivalent to the longer sides, these purple ones here, NP to RT, and that must be equivalent to these small red sides, the ratio of those MP to ST. So the ratios of the sides is proportional, and the corresponding angles are congruent. Both of those things are true because these triangles are similar, and we know that both those things are true for similar polygons. All right, let's try another problem, another kind of problems. The first problem just told us they were similar and asked us things about them. These next two problems are asking us to prove whether or not these particular polygons are similar. So to do so, the first one is to identify the congruent pairs of angles. And so we do that, we can see that the angles are in fact congruent. They have the same marks. J and T both have 2 arcs. K and U both are right angles. L and V both have 3 marks, so they must be congruent. And finally, M and angle W each have 1 mark, so they must be congruent. So for quadrilaterals in this case to be similar, 2 things have to be the case. The first is they have to have corresponding angles congruent, and these do. The second thing they need to have is to have their ratios of their corresponding sides be equal or proportionate. So let's take a look at that. The first one, the one up top, JK to TU, is 12 to 6, or 2 to 1. So if these triangles are, if these quadrilaterals are similar, then the ratio of all of their corresponding sides is going to be in that same ratio of 2 to 1. But when we look, we see that that isn't the case. The ratio of the one on the far right, KL to UV, is 24 to 16, or 3 to 2. So the top of that quadrilateral is twice as big on the left, but on the right of the quadrilateral, it's just 50% bigger, or 3/2 as big. When we compare the side LM to VW, we see that the ratio is 12 to 7. And finally, the ratio of JM to TW is just 1 to 1. They're both 6. So obviously, these shapes are not similar because the corresponding sides are not proportional. The top side is twice as big on the left, and the one on the left-hand side are equal. So you can't have polygons that are similar if one side is twice as big and the other side is equal. The ratios all have to be the same. So in this case, we can say that quadrilateral JKLM and quadrilateral TUVW are not similar because their corresponding sides are not proportional. All right, looking at question 3 here. Once again, we've got we've got triangle ABC, and now we have triangle EFG. The first thing we need to do is identify the corresponding pairs. And once again, we can see that A and D both have 2 marks, B and E each have 3, and C and F each have 1. So our diagram is telling us that these pairs of angles are congruent. So we've got the first part of our necessary proof of similarity. The angles are congruent. So the second thing we need to do is compare the ratios of the sides. So when we do that, we see the ratio of AB to DE is 12 to 15, or 4/5. The ratio, the one on the left, is 80% as big, or 4/5 as big. The ratio of BC to EF is 16 to 20. And when I simplify that, that is also 4/5, or 80% as big. And the final set of sides, AC to DF, is 8 to 10, which also simplifies into 4/5. The ratio of any side on the left is 4/5 as big as the corresponding side on the triangle on the right. So we can say that yes, triangle ABC is similar to triangle DEF, and the scale factor is 4 to 5. For every 4 inches of a side we have on the left, we have 5 inches on the side to the right. This next problem tells us once again that these particular shapes are similar, tells us that quadrilateral ABCD is similar to quadrilateral EFGD. And then it's asking us, what is the value of x? All right, so to solve that, we need to show that corresponding sides of similar polygons are proportional. And so I can see that FG is x, that's what I want, and BC, which is 7.5, that's the same corresponding side of the bigger one. And I can compare that to ED, because that has a value of 6, and DA, that has a value of 9. Now, I could have just as easily compared it to, for example, DG to DC. However, that wouldn't have helped me solve the problem because I don't have any values for that. But for DE and DA, since I know they're 6 and 9, I can use that to help solve my problem, which is now x over 7.5 equals 6 over 9. If I cross multiply, so 9x is going to be equal to 45, 6 times 7.5. If I divide by 9, I get x equals 5. So now I know that side there is 5. And although I didn't ask for it, you could also figure out the value for y here, because we know, again, that same ratio of DE to DA, 6 to 9, must be that same ratio of EF, which is y, to AB, which is 5. So once again, I could cross multiply and get 6 times 5 is going to equal 9y. So that's 30 equals 9y. If I divide by y, I get y equals 30 ninths. And then I could take that ratio of 30 to 9, and I could simplify it to the ratio of simply 10 to 3. So y is going to be 10 thirds, or 3 1/3. All right, let's go through our objectives and make sure we can do a problem of each type here. So the first objective for the day was to find the missing length of side of one of two similar polygons. So right here are two polygons, in this case triangles, and it tells us that they're similar, and it's asking us to find the length of the missing side. So to do that, the first thing we need to do is match up their vertices, or match up their sides, their corresponding sides, so we know what goes with what. So to do this it can be a little difficult, but in my head I could reflect that. Well, the first thing I need to do, is determine the corresponding sides, like I was just saying, then set up the proportion, then solve the proportion. So to determine the corresponding sides is the part that may be a little difficult. I need to take that shape on the right, and I could reflect it, put it in a mirror and reflect it, and then rotate it around 90 degrees. And when I do, now I can determine the corresponding sides. I see that the 30 side goes with the 18, and the 20 side goes with the question mark. So now I can set up the proportion. The small triangle, the big side, the ratio of that to the big triangle, the big side, or the blue over the blue, is going to have to equal the small triangle green side, or the smaller side, to the big triangle small side, which is the green side, 20. So I can put in my values by solving the proportion here. So let's do that. So 18 over 30, the blue over the blue, equals question mark over the 20, the green over the green. So now I can cross multiply. 18 times 20, which is 360, is going to be equal to 30 times x, which is 30x. Divide by 30, and I get that x equals 12. So we have solved the first of our objectives. We could find the missing side of two similar polygons. Let's take a look at our second objective, which is to find the missing length of a triangle, of a side of a triangle with a segment parallel to one of the sides. So here is a triangle, and then I've drawn this segment here, and you can see that that segment is parallel to the side of the triangle on the bottom. And when I do this, I have created two similar triangles. We'll be able to prove that in our next lesson. For now, you'll just have to trust me that indeed these two triangles are similar. So if they are, once again, I'm going to follow the same procedure I did for the last last problem. I'm going to determine the corresponding sides. I'm going to set up the proportion, and then I'm going to solve it. So the first thing to do is to determine the sides. So the small triangle, the side 5, goes with the big triangle 5 plus x. And then the small triangle 3, the side of 3, goes with the big triangle, this 3 plus 6, which would be 9. So that now lets me set up my proportion. Once again, the small side of the small triangle, the big side, compared to the big triangle, big side, is going to equal the small triangle, small side, compared to the big triangle, small side. All right, so now I can solve my proportion. So 5 over x plus 5 equals 3 over 9. Cross multiply, so that would be 45 is going to equal 3 times 5 plus x is distribute the 3, 15 plus 3x. If I subtract 15 and divide by 3, I get x equals 10. So we can see that that value is, that the missing value there is going to be 10. All right, our final objective for the day is to be able to find the variable in an expression that makes two polygons similar. So here we have two similar polygons, and I need to determine the corresponding sides, set up the proportion, and then solve it. So to determine the corresponding sides, again, these are rectangles, so I could either just rotate, or excuse me, I could either just reflect one, or I could see that the opposite sides are congruent because these are parallelograms. In either case, I can see that the top sides, which I'll put in blue, the longer side, 2x plus 20 and 35, those are corresponding sides, and the sides on the side, the 30 and the 25, even though one's on the right, one's on the left, like I said, I could either reflect one of them, or I could recognize that if these are rectangles, the opposite sides are congruent. But in either case, I'm going to set up the corresponding sides this way, so I can set up my proportion. That the small rectangle big side compared to the big rectangle big side is going to be equal to the small rectangle small side compared to the big rectangle small side. So now I can solve my proportions. So 35 over 2x plus 20 is going to equal 25 over 30. Cross multiply, and I end up with 1,050 equals 50x plus 500. If I subtract 500 and divide by 50, I get x equals 11. All right, now that we have done that, you have 3 different IXLs that you can do to show me that you can do the objectives for the day. Dilation, scale factor, and classifications with the code of ZDM or ZDM. Side lengths and angle measures in similar figures with the code of E2K. And finally, similar triangles and indirect measures with the code of JWK.